Hello, this is a short video on a couple of slides that I didn't get a chance to talk about today in our class when we introduced the effect of magnetic field on moving charge. We had two key equations so far, and if we were to have a quiz on this, and I said at the beginning, what are some questions I can take before the quiz? Here is a question that I would receive. It is, when do we use this equation and when do we use this equation? Well, this equation says that the force on a charge Q is equal to QV cross B, where V is its velocity and B is the magnetic field that it's within. And this equation over here says that the force on a wire is equal to I, the amount of current in the wire, times L cross B, where B is the magnetic field and L here has a magnitude that's the length of the wire in meters and a direction that is the direction of the conventional current flow. So when do you use this? When you're talking about a single moving charge. And when do you use this? When you're talking about a wire that is full of moving charges, a current. Here's a situation that I'd like to talk about a little bit. Let's say that I have a positive charge that is moving into a region of magnetic field with an initial speed v naught, and it's moving to the right, and the magnetic field is into the page. I'd like to ask, what direction is the magnetic force? Well, I guess if I take V cross B, then I see that the magnetic force on that moving charge points up, straight up the page. So there's FB. And so what does that do to the trajectory of the charge? Well, if there's an upward force, then in the next instant, there will still be a rightward component of velocity because it still has a rightward inertia, but there will also be an upward component of velocity because there's an upward force that created an upward acceleration that created an upward change in velocity. So I think at the next moment, the particle will have this velocity and be displaced upward a little bit from its original trajectory. Well, now what direction is the magnetic force on it? V cross B, where B is into the page, again looks like this. Note that the result of a cross product always points perpendicular to both vectors being crossed. A magnetic force is always perpendicular to both the velocity and the direction of the magnetic field. Okay, well, if that's the direction of the magnetic force that acts on it at this moment, then in the next moment, it will have, let's see, a little bit more y component and a little bit less x component of velocity. And what do we get? Well, we get a series of moments where the force is always perpendicular to the velocity. What is that a recipe for? It is a recipe for circular motion. Remember, in our circular motion unit, we always had a tangential velocity and a centripetal force that gave rise to a centripetal acceleration. And so, yes, here too, the fact that the force is always perpendicular to the velocity yields a circular path. How much work does the magnetic field do on this charge as it moves through the magnetic field? 0. Why is that? Because the force is always perpendicular to the instantaneous path. So remember, a little bit of work is equal to the force vector dot a little displacement vector, dx. Well, f dot dx is always 0 because there's a 90-degree angle, and when there's a 90-degree angle, a dot product is 0. Well, let's get a little bit quantitative. Let's say that this is a proton. No. It is a proton. No, it's, I guess this is, I think this is actually the mass of an electron. So let's say it's a positron, something with the mass of an electron and the charge of an electron, and it's moving through a magnetic field whose strength is roughly that of the Earth, 10 to the minus 4 Tesla, and let's say that it's doing this at the relatively slow 10 to the 5 meters per second. That's a little slow for a positron. What would the radius of this circle be? This is a very canonical problem that physics teachers and AP tests love to ask you, is to describe the features of the circular motion that a magnetic field brings about. The centripetal acceleration is equal to the magnetic force divided by the mass of the object. That's Newton's second law. But we also know that the centripetal acceleration is the velocity of the uniform circular motion squared divided by the radius. So if we set those two things equal to each other, then I guess the radius is equal to the mass times the velocity divided by the charge and also divided by the magnetic field. This relationship is something that a number of problems ask you to quickly derive, and you can quickly derive it by noting, v squared over r is equal to qvb divided by m, and a v cancels, and so we could ask questions like, if the magnetic field were to increase in intensity, would that result in a larger radius or a smaller radius? And it would result in a smaller radius. Great. One last example that I'd like to talk about, as we just said, that if a charge enters a region of magnetic field, it begins undergoing circular motion. So this would begin to make a semicircle once it entered the region of the magnetic field. But there's a way that you can measure unknown magnetic field strengths. And a good way to do that is to balance the magnetic field with a known electric field. So here I'm basically turning up a voltage source, maybe turning a dial on something I have in the lab that will produce a uniform electric field in this region down the page. And we could imagine that I've just turned up my dial to the point where I start noticing charges passing all the way through my apparatus instead of going into circular motion. If the charges pass all the way through, that means that the electric field balanced the magnetic field force. The electric force balanced the magnetic force because there was no net vertical force on this charge. Well, if I tell you the charge of the object and the velocity that it goes in with and the magnitude of the electric field that yields a straight through trajectory, can you tell me what the strength of the magnetic field was? Turns out you can, because here's a free body diagram. Upward magnetic force balances downward electric force. Is the electric force really downward? Yes, if this is a positive charge indicated by red, the electric force points in the same direction as the electric field. Remember that? And if the magnitudes of these forces are equal, then the charge times the electric field equals qvb sine theta. Theta, the angle between V and B in this picture, seems to be 0 degrees. So, it seems to be 90 degrees. And so the sine of it is 1. And look, the charge cancels. And there's a relatively straightforward relationship between the electric field and the magnetic field strength. The electric field divided by the velocity is the magnetic field strength. This and the last example are fairly common examples where physics teachers like to test your understanding of the magnetic field by posing this sort of setup. And this is actually this deflection of objects through magnetic fields in a way where the radius of circular motion depends on the mass is also important in what's known as a mass spectrometer, which is a device that chemists use to measure the mass of unknown compounds.